next section is just solving systems of equations in 3 variables. Okay, so we're going to do the same thing that we were doing. We're going to do the same thing we were doing, just using 3 equations in 3 variables now. Okay, so an equation with 3 variables just represents a function in 3-dimensional space. So a solution for a system with 3 variables is just going to be written as ordered pair like this. Okay, x, y, z. So the visual for graphing in 3-dimensional space, okay, we still draw our x and y coordinates, but then I'm going to draw a z coordinate that's kind of coming out of the board. Okay, so you have to think about this as 3 dimensions. Right? So this is my z-axis. So if I wanted to plot the points, I don't know, like 1, 2, 3. Okay, well, I'm going to go 1 on the x, then 2 on the y, and then 3 on the z-axis. So we kind of have to think about, well, I'm going to go out 1, 2, 3 on the z, and then 1 on the x, and 2 on the y. So I'm going to be, it's a little tougher to visualize in 3-dimensional space, okay, but we're going to be coming 1 on the x, 2 on the y, and then 3 on the z. Right? So we can kind of say, well, this point is going to be here, here, and then I'm going to go up 2 spots. Okay, I know it's tough to visualize when you're trying to do 3 dimensions on 2 dimensions. Not making stuff up. So I went 1 on the x. Okay, so 1 on the x is here. I went 3 on the z. Okay, so 1, 2, 3 on the z. So that point where those 2 things would meet is like right here somewhere, and then from there I went up 2 spaces. Okay, I know it's hard to visualize graphing in 3 dimensions when you're trying to do it on 2 dimensions. Okay, but that's the idea. Okay, we're extending now to 3-dimensional space. Right? So
That sucks.
It does.
we're gonna have systems that look like this now. Okay, 3 equations with 3 variables. Okay, we could have 4 equations with 4 variables. We could have 5 equations with 5 variables, right? We could keep going up and up and up in dimensions. Okay, but we're gonna stop at 3. So first, just to determine whether an ordered triple is a solution, okay, just like we did for 2 variables with 2 equations, I'm just going to plug these values in. Okay, I'm going to plug 2 in for x, -1 in for y, and 3 in for z, and see if we get 3 true statements. So 5 times 2 plus 3 times -1 minus 2 times 3. We want to know if that equals 1. Right, so we've got 10 minus 3 minus 6. That does equal 1. Okay, so the first one works. Second one, 2 minus -1 plus 3. We are hoping that equals 6. So 2 plus 1 plus 3 does equal 6. That one works. The last one, I plug 2, -1, and 3 in. 2 times 2 plus 2 times -1 minus 3. So 4 minus 2 is 2. Minus 3 is -1. Okay. So since all 3 of those work, 2, -1, 3 is a solution. What that means is if I were to graph these 3 lines in 3-dimensional space, they would all intersect at this point.
Since unless lines are parallel, they're always going
to intersect somewhere on a two-dimensional graph?
Right.
Is it a lot harder for them to all intersect on a three-dimensional graph?
It is, yes. That's a good question. Okay? If we graph 3 lines in a 3-dimensional space, right? If we just pick 3 random lines, odds are they're not all going to intersect at the same point, right? In a 2-dimensional space, if we just pick 2 random lines, odds are they would intersect, because the only way they wouldn't is if they're parallel. But in a 3-dimensional space, we could have lines that are skewed, okay, meaning they don't intersect, but they're still not parallel. Okay?
I feel pretty skewed today.
Okay, questions so far? All right, so let's start taking a look at solving systems then. So this first one, okay, we've got 3 equations, okay, but not all 3 variables are in each equation. So this one is actually pretty simple to solve. This one, z is almost already solved for us. Okay? To solve for z, okay, in something like this, I would just have to take this equation and divide by 2 and get z equals 3. Right? So now, once I have one of my answers, I can just start plugging it back into previous equations. Okay, so now I can take this middle equation and plug 3 in for z. So we can say 2y plus 3 times 3 equals 5. So 2y plus 9 equals 5. Subtract the 9 over. Divide by 2. So now I can take both of these answers and plug them into my first equation that has x, y, and z in it. So I can plug 3 in for z, negative 2 in for y. So I'll have x minus negative 2 plus 3 equals 6. So this would be plus 2 plus 3. Right? So this would really be x plus 5 equals 6. Subtract the 5 over and we get x equals 1. So we want to write our answer as an ordered triple. And so my answer is going to be the points 1, negative 2, 3. Right, so when you're writing your ordered triple, make sure that you're putting things in the correct order. Right? X, then Y, then Z. Okay, so a system like this, okay, where all we have to do is substitute things back in, is pretty straightforward. Okay? Any questions on something like that? Probably. They're not ungodly hard. They're a little bit more challenging.
Are they godly?
Sure. Okay, so now, the next few examples, we have all 3 variables and all 3 equations. Right? To solve something like this, we want to eliminate some of the variables, just like we did for systems of 2 equations and 2 variables. I want to add equations together to eliminate variables. Right? Now, there isn't I shouldn't say that. There is a way that will work every time. Okay, but if we use a little bit of strategy, we can save ourselves a decent amount of work sometimes. Okay, so if I look at these 3 equations and I think about adding some of them together, okay, we can only add 2 together at a time. But if I look at the second 2, or the second and the third equations, if I were to add these together, y's would cancel and the z's would cancel, right? So if I take these 2 equations, right, just the second and the third ones, and add them together, I'll just end up with 3x equals 3, right? Because y's would cancel and the z's would cancel. Well, then if I divide both sides by 3, I'll just get x equals 1. So now, I can take this answer of x equals 1 and plug it into any or all of my previous equations. Okay? The goal is usually going to be to create a system of 2 equations and 2 variables. Right?
Shifted a little bit.
So if I take this value of 1 and plug it back into one of my, I don't know, let's do it in the first 2 equations. Okay, if I plug 1 in for x here and 1 in for x here, that's going to create 2 new equations. So this will be 1 plus y plus z equals 6, and 1 minus y plus z equals 2. So then, if I subtract the 1 over on both of these, I'll have y plus z equals 5, and negative y plus z equals 1. Okay, so far? So now, I can take these 2 equations and add them together. So, as they are now, the y's would cancel, so I don't have to do anything crazy. I would just get 2z equals 6. Divide both sides by 2. Z would be 3. So now I've got 2 of my coordinates. I can take those and plug it back into, I can do one of my original equations, or I could actually just plug z equals 3 back into one of these equations to solve for y. So, I don't know, if I plug z equals 3 into this first one, I'll have y plus 3 equals 5. Subtract the 3 over, and we'll get y equals 2. So, my solution is going to be the points 1, 2, 3. Okay, so the goal, okay, is just to start eliminating variables and creating new equations. Okay, essentially, we're going to want to create a system of 2 equations and 2 variables that we can then solve. Okay, like we just did yesterday. Questions so far? All right, let's do another one together here. Let's take a look at B. Okay, in this one, if I look at any of my equations, and I think about adding any of them together, there are no variables that would just cancel out. Okay? So, what we can do is multiply one or both of equations by a constant, just like we did for systems with 2 variables. Okay, so it does not matter which variable I choose to cancel out. Let's say I'll look at the first 2 equations and I will eliminate y. Okay, well, if I want to eliminate y, it would probably make sense to multiply this first equation by 2. Right? Then I'll have negative 2y and positive 2y. So I'm just going to take this entire first equation and multiply it by 2. So that will get me 10x minus 2y plus 2z equals negative 34. Okay, so I'm not going to change my second equation, okay, because that 2y will cancel out. So now I'm just going to take 2x plus 2y minus 3z equals negative 3. And I'm going to add those 2 equations together. So I'm going to get 12x minus z equals negative 37. Okay. So now I want to create another equation where I eliminate the y. So I'm going to go back to my original system here and pick out two other equations, right? So I could do the first and the third one. Okay, if I want to again eliminate y. Okay, we have to eliminate the same variable as we did for the first equation, so that I can create a system of equations that has the same two variables left. Right, so yeah, let's say we'll look at the first and the third equation. Okay, so now if I want to eliminate y's, well, I would probably want to multiply the first equation by -3. Okay. So if I multiply this one by -3 this time, I'll come over here then. That'll be -15x plus 3y minus 3z equals 51. And then I'm just going to take the third equation as is. So x minus 3y plus 2z equals -10. Add these together. So I will get -14x, y's cancel, minus z equals 41. Okay, so I've created two equations now that just have x's and z's. Okay, two equations that have the same two variables. So now I'm going to solve this system of equations. Okay, so I'm just going to take these two and rewrite them down here. So 12x minus z equals -37, -14x minus z equals 41. Okay, well, it looks like the z's will probably be the easiest to eliminate in this system. Okay. So I would just need to multiply one of the equations by -1. And so I'll do the first equation. I'll multiply this whole thing by -1. So that would become -12x plus z equals 37. We'll leave the second equation alone. So now I can add these two together. -26x. The z is canceled. And 37 and 41 is 78. Divide both sides by -26. That gets me -3. Okay, so now, once I have one of my coordinates, I can just start plugging things back in. So now I can take this and plug it back into one of my two equations that has just two variables. Okay, it doesn't matter which one. I'll plug it into the first one. So we have 12 times -3 minus z equals -37. -36 minus z equals -37. Add the 36 over. Divide by -1. We get z equals 1. So now I can take both of these and plug them back into any of my original equations that has all three variables to solve for y. So it doesn't matter which one. I'll plug it into the first one, I guess. So 5 times -3 minus y plus 1 equals -17. So -15 plus 1 would be -14. So -y minus 14 equals -17. Add 14 over. Divide by -1. So my answer would be the ordered triple, -3, 3, 1. So again, the goal is just to create a system of two equations and two variables. And we can do that using any combination of our original equations. And then we can just solve that system of two equations and two variables. And then work backwards to get all three answers. Questions on that one?
I did not like doing that.
It's a decent amount of work. Okay, but does it make sense?
In the same way that cutting your arm off when it gets stuck in a rock makes sense. You might have to do it, but you don't want to do it.
Okay.
Basically, what I'm trying to say is that this is like cutting my own arm off.
But you know how to do it, and you're willing to do it to survive.
Yeah.
All right.
Thank you.
So let's do one more. Okay. So let's go through the same process here. I want to try to eliminate one variable. So if I look at my first two equations and I add those together as is, the y's would cancel. So let's use those first two. Okay. So if I add those together, x and 2x would get me 3x. The y's would cancel. 2z and z would be 3z. And then 5 and 7 would be 12. Okay. So now we want to create another equation that's got just x's and z's. Yeah. So we can choose again any two equations. To eliminate y from. So if I choose the first and the third, or the second and the third, I'm going to have to do some kind of multiplication. So it doesn't really matter what combination I choose there. So I'll do the second and the third. So if I just multiply this second equation by 2, the y's will end up canceling. And so I'll do that. So I'll rewrite this over here. This would become 4x plus 2y plus 2z equals 14. And my second equation, 3x minus 2y plus 5z equals 20. So now if I add these together, I'll get 7x, the y's cancel, plus 7z equals 34. Okay, so now I have two equations and two variables. So I'll rewrite those down here. So 3x plus 3z equals 12, and 7x plus 7z equals 34. So to solve a system like this, okay, it doesn't matter which variable I choose to eliminate, but under the foolproof way, when we've got ugly coefficients where there isn't a nice way to just multiply one of them to get a variable to cancel out, is to just, so if I want to eliminate the x's, I'm just going to multiply this top equation by 7, the bottom equation by 3, and we just need to make sure that one of them is an opposite sign, right? Everything's positive right now, so I would just need to make one of these negative, so that the x's would cancel. So these equations will become negative 21x minus 21z equals negative 84. And then this one would become 21x plus 21z equals 102. So now, if I add these together, well, the x's cancel, and the z's cancel. So we're just left with nothing over here.
Oh no.
Oh no. Equals 18.
That looks correct.
What happens if I get something like this? There'd be no solution. Okay? So obviously this is not a true statement. So if we ever get an untrue statement like that, there are no solutions.
Ooh, cool.
Questions?
Why do I keep getting working emails?
I don't know.
I'm gonna put them in my spam folder. I probably got 115 in the last week.
Alright, let's take a look at one last problem here. Okay, for this, we want to set up the system, but we're not going to solve it. Okay, so we get a story problem. Alex, Becky, and Courtney. They're stuffing 741 envelopes for Senator Douglas's re-election campaign.
Woo!
Alex can do 124 an hour, Becky 118 an hour, and Courtney 132 per hour.
Got nothing on Courtney.
They worked a total of 6 hours. The sum of the number of hours that Becky and Courtney spent was twice what Alex spent. How long did each of them work? Okay, so we want to figure out 3 equations here. Okay? I want to set up 3 equations. So first, let's come up with our variables. So let's say that x is the number that Alex can stuff, y is the number that Becky can stuff, and z is the number that Courtney can stuff. So how can I come up with an equation here? Wait a minute. I guess
Let's do 740 equals.
I guess this shouldn't be the number of envelopes. This should be the number of hours. Sorry, not the number of envelopes, because we want to figure out how long each of them worked. So this should be the number of hours, not the number of envelopes.
Oh no.
We'll say hours for Alex, hours for Becky, and hours for Courtney. I didn't read the last line of the problem. We want the number of hours.
So you set it like 741 equals 142x plus 118y plus 132z.
Yeah, so my first equation could be 124x plus 118y plus 132z.
I don't know what the second one would be.
124x plus 132z equals 741. So then the next piece of information they give us is that these 3 worked a total of 6 hours. Yeah, so then we could say x plus y plus z equals 6. The last piece of information we have is that the sum of the number of hours that Becky and Courtney spent was twice what Alex spent. How would I write an equation like that? So y plus z, where'd you get 12? 2 times the amount of hours that Alex spent.
So can you put like x plus 2x equals 6 or something like that?
Well, I think this last one is just going to have x, y's, and z's. I don't think we're going to use the total number here. So yeah, I think we can say y plus z equals 2x. Okay. So the sum of the hours that Becky and Courtney spent was twice what Alex spent. So I would need to multiply the number of hours that Alex spent by 2 to get what Becky and Courtney works. Okay.
Bro, Becky be working hard.
Well, I mean, in theory, this could all be. Well, no, they could all work pretty close to the same amount using that equation.
Mr.
Not
Fetch,
exactly